Alright, today we're going to talk about the mean value theorem, but for integrals. We've already talked about a mean value theorem, but with derivatives. So now we're going to look at the mean value theorem for integrals. So then really the gist of this mean value theorem, what it's going to talk about, and I'll show you some more parts to it. Really, we're just looking at when we have a rectangle that is inscribed within our curve, we're typically underestimating the area because there's parts of the curve that go above the rectangles, and if we have a rectangle that's circumscribed or on the outside, parts of it go on the outside of our curve, we overestimate it. This mean value theorem for integrals just tells us that if we have those two rectangles, there has to be another rectangle somewhere between them that gives us the exact area under the curve. In other words, we can say that the area of a region under a curve is greater than the area of that inscribed rectangle. It's also less than an area of a circumscribed rectangle. Really, that's all we're looking at. The mean value theorem then tells us there's a value somewhere between those two rectangles that will give us the precise area. Now, the actual mean value theorem states if we have a function that's continuous on a closed interval, then there's a number, there has to be a number, c, within that interval, such that when we take the integral, the definite integral from a to b of our function with respect to x, we're going to get f of c times our change in the interval, b minus a. All this really means is this mean value theorem is not going to give us a way to find that c value. It just gives us a way to show that there is a value somewhere between a and b. Now, we're also going to talk about an average value of a function. And we can say that the value of a function at c given in the value of f of c given in that mean value theorem for integrals is called our average value of f on the interval from a to b. Then we have a little kind of theorem here. If f is integrable on a closed interval, then the average or the mean value of f is taking the integral from a to b of our function with respect to x and multiplying it by 1 over b minus a. We can also write it as just taking the integral divided by b minus a, which takes our area over our width and gives us an average height. So let's get into some examples. So example 1, we're going to be given the function 3x squared minus 2x, and we want to find the average value of f on the interval from 1 to 4. So we're going to use that average value theorem from before. We're going to take 1 over, in fact, we're going to take the integral from a to b of our function with respect to x over b minus a. And I'm going to just replace that with the values we're given. So we're going to take the integral from 1 to 4 of 3x squared minus 2x with respect to x over 4 minus 1. which means we're going to take, first we'll integrate our numerator, 3x squared. When we take the integral of that, we'd have x cubed minus x squared from 1 to 4 over, well, 4 minus 1 is 3. So let's clean this up. Our numerator, we can rewrite that as 4 cubed minus 4 squared minus 1 cubed minus 1 squared, all over 3. So 4 cubed is 64, 4 squared is 16, and 1 cubed is 1, 1 squared is 1. If we went 1 minus 1, we'd get 0. So we're going to end up subtracting 0. I'm not going to write that. So over 3, and then 64 minus 16, that is 48. So we have 48 over 3, which we can simplify to 16. So the average value of f within the interval from 1 to 4 is 16. We can say that that is an f of c value. So now we want to figure out what values of c could potentially give us 16. So we're going to take our 3x squared minus 2x and just replace the x's with c. So 3c squared minus 2c, and then set that equal to 16. Now to solve this for c, I'm actually going to move my 16 over. So I'm going to have 3c squared minus 2c minus 16 is equal to 0. And then I'm going to factor it. And I'm going to show you a method that when I'm teaching middle school, I use to factor. It's called this AC slide method. So I'm going to make this x. And up at the top, what I'm going to do, and I like using this method when I have a number that's in front of the quadratic term. So I'm going to go 3 times 16, which is 48, and that's technically a negative 16. So I'm going to write a negative 48 up here at the top. And then down at the bottom, I'm going to put a negative 2, our middle coefficient. Now some tricks that I know about factoring is if I have a minus sign here at the end, I need one positive and one negative factor. Positive times a negative is how we make a negative. So now I ask myself, numbers that I know multiply to make 48. 1 and 48, 2 and 24, 3 and 16, 4 and 12, and 6 and 8. So I'm looking for which pair will add to make a form of 2. Well, if I have a positive 1 and a negative 48, that's going to give me negative 47, which is not what we want. If I had a 2 and a 24, I get a negative 22. Again, not what we want. 3 and 16 would give me negative 13. Not what I want. 4 and 12. We're getting closer. That gets me a negative 8. But that's not what I want. 6 and 8, that gets me negative 2, which is what I want. So now when I'm setting up my factors, I'm going to have a 3c in both of them. And I'm going to have to do some simplifying in a bit. I'm going to put a plus 6 and a minus 8 into those. And then I set these to 0. However, in this first set of parentheses, the 3c and the 6 are both divisible by 3. So I need to rewrite that as c plus 2. I need to divide that 3 out. And now what I'm going to do is I'm going to take each factor and I'm going to set it to 0. c plus 2 equals 0 and 3c minus 8 equal to 0. And I'm going to solve them. So with this first one, I'm going to subtract 2. c would equal -2. And in the second one, I'm going to add 8, have 3c equals 8, and then divide by 3, and get c is equal to 8/3. Now, only one of these numbers is in the interval from 1 to 4. That's the number we're going to use, and that is 8/3. So we cannot use -2. It's not between 1 and 4. So now let's look at example 2. So example 2, we have in the year 2000, the world's population was 6.1 billion, and the relative rate of growth was 1.4% per year. And we can model, or it can be modeled by the function 6.1 times e to the 0.014t, where n is people in billions, and t is the number of years since 2000. We want to assume this model remains true until the year 2050, or we're going to assume that. And then we want to find the average population of the world between the years 2010 and 2020. And what are those units? So using that average value theorem, we're going to take the integral from 2010 is 10 years after 2000, to 20 of 6.1 e to the 0.014 t dt over 20 minus 10. Now, rather than rack my brain as to how to integrate this, in my numerator, I'm actually going to just use my calculator to find that value. So when I do that, in my graphing calculator, I get about 75.3158. It goes a little further than that, but we're just going to go to the 3158. And then 20 minus 10 is 10. So we're going to divide this numerator by 10. We're going to get 7.53158. Or what we're saying is we have an average of about 7.532 billion people. For the years 2010 to 2020. So now let's look at example 3. So we are going to suppose we have a function c of t, which represents the daily cost of air conditioning at your house in dollars per day, where t is the time in days and t equals 0 corresponds to the date July 1st, 2017. Let's explain what the following expressions represent in real-world terms, including the units. So with this first one, a, the integral from 0 to 90 of just the function, this represents the total cost to cool your home for July 2017, and then 90 days after that would be September, so to September 2017. Not too bad there. With this second one, if we're looking at 1 over 90 minus 0, just multiplying part A by 1 over 90, then this is going to be looking at the average cost to cool your house in dollars per day for 90 days from July 1st, 2017. And that's it. And as I look at our next example, I think I'm going to need more time than I have to record this section of the videos. So we'll pick up on our remaining examples, our remaining stuff in our next video.